Hey guys, welcome back to another law of conservation of energy problem. A 0.610 kilogram block is firmly attached to a very light horizontal spring, K equals 170 newtons per meter, as shown below. It is noted that the block spring system, when compressed 4.5 centimeters and released, stretches out 2.1 centimeters beyond the equilibrium position before stopping and turning back. What is the coefficient of kinetic friction between the block and the table? Okay, so here's the picture we're given. We're given our table, we've got our block, the spring, and it's attached to the wall. So there are two instances which we're dealing with. The spring is compressed with the block and then it's let go and it extends beyond the equilibrium position. So I'm going to draw myself two more instances so I can compare the positions of the block with the spring. Okay, so in the first instance here, we've got our block compressed a bit. So let's draw the spring compressed and draw your block right after. And then after it's compressed, it's let go and it stretches beyond the equilibrium position. So now you want to draw your spring stretched a bit. And I'm now going to draw some vertical dashed lines so I can compare these distances. For example, this is the equilibrium position. So I'm going to call that x equals to 0. Okay, then we know the compression is over here. So let's draw another line here. That's going to be x1 is equal to minus 4.5 centimeters. I'm saying minus because it's to the left of the x equals to 0. And finally, I've got this position right here. Okay, this is after it extends past the equilibrium. I'll call this x2 equals 2.1 centimeters. So if you look at it, we're looking for the coefficient of kinetic friction. Obviously, there is friction on the block. Because you're compressing it at 4.5, it's only extending out 2.1, right? So there has to be something opposing it, slowing it down. However, when you let it go at this point, it's moving forward past the equilibrium to this end point. So the total distance over which friction is acting, which we're considering, is this total distance. So we can say that friction acts over 4.5 centimeters plus 2.1 centimeters, which is equal to 6.6 centimeters. So that's going to be our distance over which friction is occurring. And in this problem, the whole goal of this is to look for mu k, the coefficient of kinetic friction. So because this is a law of conservation of energy problem, I'm going to solve it using the work energy theorem. So up until now, we've looked at work equals the change in kinetic energy. However, in this question, we not only have kinetic energy changing, we also have spring or elastic energy changing. So what I'm actually going to do is set the work equal to the change in spring energy. Now, the work done by what? Well, the spring energy is changing due to friction. Okay, so I'm going to say the work due to the frictional force is equal to the change in spring energy, and I'm going to analyze the relationship between those two. Okay, so the work due to friction, work is equal to force times distance times cosine of theta. And since we're dealing with friction here, this is going to be force of friction. Okay, delta ES, it's just like delta EK. It's EK2 minus EK1, or in this case, ES2 minus ES1. Okay, so to figure out the angles, take a look at this. Okay, so when you release the block at this position, it's going forward, right? So the distance is going in this direction, but friction's opposing it. Friction's going in the opposite direction. So the angle between those two is 180 degrees. So cosine of 180 is minus 1. So this thing disappears and you're going to get minus 1. So the next line you're going to have minus FFRD equals ES2 minus ES1. Well, this is actually really cool. The formula for spring force looks almost exactly like kinetic energy. Sorry, spring energy looks like kinetic energy. So 1/2 kx2 squared minus 1/2 kx1 squared, where k again is the constant. The x's are the amount by which the spring is either compressed or stretched. Okay, next, I want to substitute for this force of friction. We know the force of friction is the product between coefficient of friction, in this case it's kinetic, and the normal force. Okay, so mu k. Now, instead of writing Fn, in this question, you've only got two vertical forces. Although I didn't even draw a free body diagram, it should be clear that the only vertical forces acting here are normal going up and gravity going down. So I can actually replace the Fn with mg. So mg, and then you've got your d there. Don't forget that. On the right, I'm going to factor out 1/2 k, and then I'm going to have x2 squared minus x1 squared in brackets. So let's actually start plugging in our values. Okay, so let's leave the left side as is. Oh, I forgot the negative sign. Okay, mu k mgd equals, so 0.5 for the half, k is 170 newtons per meter. Okay, x2 is 2.1 centimeters. Remember, this is a physics problem. You have to plug it in meters, right? So it matches up with the units here for k. So we're going to do 0.021 meters squared minus, and then x2, or rather x1 is negative, so negative 0.045 meters squared. Notice it doesn't really matter that it's negative, because when you square it, it'll become positive regardless. Okay, so when you solve this entire right side, you are going to get minus 0.13464. Now that's equal to minus mu k mgd. If you want to just solve for mu k right on the spot, or minus mu k, you can just divide both sides by mgd. Okay, so the mass is 0.610, right? They tell you in the question. So let's plug those in. 0.610 kilograms. G is your handy 9.8 meters per second squared. And finally, d, the distance, we said it was 6.6 centimeters, or expressed in meters, 0.066 meters. Okay, so there you go. I just took what I had on the right. That's this number. I divided it by m times g times d. That's what's down here. So notice I've got a minus on both sides. That'll cancel, which it should, because you can't have a negative coefficient of kinetic friction. When you punch all this in your calculator, you are going to get mu k equals 0.34. Okay, so there you have it, guys. There is your coefficient of kinetic friction. Hope you guys enjoyed the video. If you do have any questions, be sure to leave them in the comment section below. Otherwise, be sure to smash that like button to tell me if you guys like the video and if you're learning things from it. Otherwise, I will see you guys in the next video, 115, posted tomorrow at 12 noon. Hey guys, that's it for this episode. If you enjoyed it, be sure to check out some of my most recent videos posted over there on the right, which you can click on your screen right now and watch. Other than that, guys, I hope you enjoy the rest of your day, and I will catch you in the next video. Is the end screen too long this time? Wait, you're still recording? No! Oh. Gotta move that chair out of the way next time.